We already talked about the density, which is we use rho for density. This is the notation. Mass over volume. Pressure, we use P for pressure. Force over area. And also we talk about atmospheric pressure at sea level, which is 1.013 times 10 to 5 Pascal. Pascal is the SI units of pressure. We know newtons per meter square is the same as Pascal. You know, SI unit is Pascal, but pressure is force over area. Force of units of force is Newton. Area is meter square, so we call it Pascal. And and then we also derive a relationship between pressure and depth. Pressure at two different levels. Pressure at bottom is equal to pressure at top times rho. Density of the fluid. Height is the height difference. H is the height difference between P1 and P2, and G is the gravity, which is 9.8 meters per second square. And then we talk about Archimedes' principle, which says the buoyancy force is equal to weight of displaced fluid. Buoyancy force is equal to F. We use F for force, and we use subscript B, which indicates buoyant force. Buoyant force or buoyancy force is equal to weight. We use W is for weight, which is mass times gravity. If you know the volume, we can calculate the weight or the mass, and then weight of the fluid or weight of displaced fluid, which is equal to the buoyancy force. So in this example, you see a raft um, uh, on water surface, and depending on the we know this raft has a weight which is always pointing down, mass of the raft times gravity. And also we just talk about buoyancy force, force from the water on the raft. So if buoyancy force, this force is greater than weight, if this is the case, if buoyancy force is greater than the weight, this raft is floating. If both forces are equal and opposite direction, buoyancy force is same as weight, then it will stay at equilibrium, so it is stay at same level. If weight force is greater than buoyancy force, then weight is greater than buoyancy, therefore it sinks. So, so we can calculate the buoyancy force, which is equal to weight of displaced fluid, and if you know the volume of the raft, the dimensions are given with height and depth, and if you know the volume of the raft, and if you know the density, because of the raft we displace some water, so if you calculate the weight of the water displaced due to the volume of this raft, we can calculate the buoyancy force. So density of water is 1000, we know that, and we calculate the volume in over here, which is 4.8 cubic meters, and G is 9.8. So buoyancy force is 47,000 Newton. Uh, volume, weight of the raft is mass of the raft times gravity. So if the mass is not given, we can calculate because we know density is mass over volume. We already know the volume of the raft, so mass of the raft is density times volume. So density is it's made out of pine, so density of pine is 550 kilograms per meter cube, and volume, which is we calculate in the previous page, 4.8 cubic meters, and G. So if you multiply these three together, you get weight is 26,000. Clearly, the the buoyancy force Fb is greater than weight. Therefore, the raft floats. In previous example, we learned that buoyancy force is equal to weight of displaced fluid. So if the buoyancy force is same or little bit greater than the weight, we can keep an object on the water. So ship, the buoyancy force on the ship is the volume or weight of displaced water. So this figure shows the volume of the displaced water. So the question is, can an ocean vessel float in the amount of water than a swimming pool contains? If the swimming pool has capacity to hold more than this volume, then this ship can float in a swimming pool, because only thing it uh, consider uh, needs to consider is the weight force, which the buoyant force, the force from the water on the ship, which is equal to the displaced water, uh, volume, weight of the displaced water. If these two are same, whether it's on a swimming pool or in a ocean, it doesn't matter. So if the pool has enough capacity to hold more than you know volume of displaced water, then swimming pool can and float a, a vessel. Okay, so fluid in motion. So we're going to talk about the difference between steady flow, unsteady flow, and turbulent flow. So steady flow, as it states, if you have any fluid molecules and if they are moving with the same speed or velocity, since they are in the same direction, it's the same velocity, then we call it steady flow. Unsteady flow is if they're in the same direction, but the velocities can change, which means they have a acceleration, so or deceleration. So here it's slow down, here it's speed up. So unsteady flow is when the velocity of fluid particles at point change as the time. So with the time, it can slow down, it can speed up, it can slow down, so then it become unsteady flow. And even if you consider these two, and if you want to solve a problem, and here acceleration is 0, and here we have acceleration. So turbulent flow, it can, these particles, molecules can move any direction. So if we have a problem like this, and if you want to solve for speed or velocity or position, it's very difficult, because these particles move all over the place and different directions. So in this section, we're going to derive a equation with pressure and speed and energy. So we're going to make some assumptions so that it's easy for us to derive a equation, and that's why we're going to talk about these three terms, steady flow, unsteady flow, and turbulent flow. And we, based on these definitions, we're going to make some assumptions before we derive that equation. Okay, compressible and incompressible fluids. So, so we know density of a fluid, rho, which is equal to mass and volume. So if a fluid can compress, which means we can change the volume. If we can compress, which means we change the volume, or we decrease the volume, which means we increase the density. So there are fluids, it can compress, most of the fluids are incompressed. We cannot change the volume, which means the density remains same. Density is not going to change. And also two more notations, viscous and non-viscous. Viscous is resistance to flow. So if you pour like water, let's say you can compare water and like oil. So we know oil clearly has some resistance to flow. So so non-viscous. So no resistance to flow and incompressible. The density is not changing. We call it ideal fluids. Ideal fluids are non-viscous. They flow freely, no resistance, and incompressible. The volume or density remains same no matter what the speed or what's the temperature, these of the fluid. The density and volume remain same. So ideal fluids are non-viscous and incompressible fluids. So we talk about steady flow. Steady flow is the fluid particles maintain same velocity, and we can use line like this streamline to show the trajectory of the fluid for particles. So if the motion is steady, the velocities are same, and we can use lines to represent a streamline or steady flow. The mass flow rate. So flow rate is rate of change of flow as a function of time. So mass change. So if you use a water flow, we can measure the mass of the water, mass of the water, mass of the water flow in a certain period of time. So then mass over time, we call it mass flow rate, rate of mass, change of mass over time. Okay, in this figure, you see a tube. One side has a higher diameter compared to the other end of the tube, which is side one has a lower diameter. So it's a one tube, but the diameters of the either side is one side is higher and the other side is lower. So we're going to uh, derive a equation to calculate the speed of fluid particle in this traveling from side 2 to side 1, because we know there's a pressure difference between the two sides because of the diameter change, and of course the cross-section area of side 2 is greater than side 1. So uh, so in order to derive this equation, we call it continuity equation, because it's a continuous flow of fluid. So we're going to take mass flow rate we talked about last in the previous page. uh, cha Change rate of change of mass. Now, if you consider a small mass delta m in this area 2, we can write delta m2, and that mass, rate change, we can write in terms of rho v, because we know rho is the initial equation is density, rho is equal to mass over volume. So mass is rho times volume. So volume we can write in terms of the cross section, A times area. Area A is the area, and then this side length or the distance. So distance is we can write in terms of speed and time, because we know distance, speed or velocity. Speed is distance over time. So distance is speed times time. If you know the speed of the particle, let's assume v2, and the particles on this side move to this side in delta t time, we can write instead of v distance, we can write time times speed, v delta t. So this is a general equation. The mass, small mass delta m, cross from one side of this side to the other side. We can assume delta m, or the mass and area uh, and speed and delta t. So don't be confused with the notations. Here this equation v is volume, but we replace the volume in terms of speed or velocity and time. So if I rewrite delta t and delta m over delta t, we have on the opposite side a rho av. Okay, so this is v. So delta m over delta t is density of side 2, area, cross-section area of side 2, and speed or velocity. Density, area. Okay, same thing here, the same mass. So, if you consider a mass traveling from one end to the other end, mass change, mass flow rate is density of the fluid in area 1, it's a cross section of area 1, and the speed of these fluid particles in area 1. So delta m over delta t is rho 1 a1 v1. So the equation of continuity, the mass flow rate has same value, delta m 2 over delta t is same as delta m1 over delta t. So all the water molecules or fluid molecules in this area 2 needs to cross this area 1 during a given time, so that all the molecules fluid molecules pass from area 2 to area 1. At every position along the tube has a single entry and single exit for fluid flow. If these two are equal, which means rho 1 a1 v1 is equal to rho 2 density a2 v2. So this is the equation of continuity, and we can simplify this equation a little bit more, because we know same fluid pass from 2 to 1 area, 2 to area 1. So if we assume this fluid is incompressible, so we know volume is density is mass, so volume. If incompressible, which means we cannot change the volume, which means density is same. So the density of the molecules, fluid molecules in site 2 or area 2 is same as the density of the same fluid, and if the fluid is incompressible, we cannot change the density. So therefore density 2 is equal to density 1. So we can cancel these two, and therefore area of v1, area of one side, and the speed of those fluid molecules on that side is equal to area of the opposite side and the speed of the fluid molecules on the opposite side. So the initial equation was rho 1 a1 v1, rho 2 a2 v2. V is speed or velocity. Okay. Velocity. Rho is the density, A is the cross-section area. So incompressible fluids, these two are same, so they cancel. A1 V1 area times velocity is equal to area on the opposite side times the velocity of the fluid molecules on that side. So A times V, area times speed, we call it Q. It's a volume flow rate. It's a notation. Q is volume flow rate, which is equal to area times speed or velocity. So here's an example. The first figure, the one on top, shows a garden hose with the full opening, and you see water coming out. And when you put your thumb in front of this opening, you see the water flow rate goes up. So the area, it's, here we have a larger area, and the uh, speed is smaller, and we have a smaller area. And if the area is small and the velocity goes up, if the area is large, volume velocity goes down, and if the area is small, cross-section area is small, the velocity of the fluid is larger. So in this example, it says garden hose has an unobstructed. If it is fully open, the cross-section area, which is A2 in our drawing, is given, and it fills a bucket with a volume uh, 8 times 10 to negative 3 cubic meters in 30 seconds. So from this information, we can find the Q, volume flow rate, which is equal to area times V. And part A is find the speed of the hose. Find the speed of water that leaves the hose, the unobstructed opening. So V, so Q is 8 times 10 to negative 3 cubic meters divided by 30 seconds, which is equal to cross-section area is 2.85 times 10 to negative 4 square meters. This is Q is cubic meters over second in square meters. So your final answer is flow rate meters per second, and I'll show you the answer for times V. V is the velocity of the water. Okay, so when you solve that equation, V, unobstructed area, the water coming out of 0.936 meters per second. And part B says if you obstruct the surface cross section, what is the speed? So you can use area times velocity, which is equal to area times velocity on the opposite side. So if you want to calculate the velocity on the opposite side, you need to know the unobstructed area, which is given, and therefore you can calculate V, and which is equal to 1.87. So you can clearly see this number and this number. When you obstruct the opening, the speed goes up. Okay, so from the previous example, we see that when the opening is smaller, we have a large velocity of the fluid molecules or particles, and if the area is cross-section area is large, we have a smaller speed. And same thing here from we learn a pressure depth equation. P2 is equal to P1 plus density, height, and gravity. So if you compare the pressure 2 in this side and pressure 1, so pressure 1 is always low compared to pressure 2. Pressure 1 plus rho hg. So we have to have a rho density. It's like a potential energy term. Remember, potential energy we derive like mass, gravity, and height. So since we're talking about fluid, we talk about density, height and gravity. So it's like a potential energy. So pressure here is equal to pressure here plus potential. So basically P2 is greater than P1. So we're going to derive another equation. It's called Bernoulli equation. It has the speed, pressure, and it's basically a conservation of energy. We learn in previous chapters, and we can apply the same principle for fluids, and we're going to derive a equation. We call it a Bernoulli equation. To derive a Bernoulli equation, I'm going to write two equations we learned in previous chapters. Work we define as net force times displacement. Okay, and and similarly we wrote force work in terms of kinetic energy change plus potential energy change. So kinetic energy associated with the moving fluid particles, because if a fluid particle has a velocity, which means it has a kinetic energy, because kinetic energy is half mass and velocity square. So if there's a velocity change, we know there's a potential energy change, because we know the velocity here, the area which has a smaller cross section has a higher velocity. Here we have a large cross section, which means higher velocity. So therefore velocity change means we have a potential kinetic energy change. Similarly, we know potential energy is associated with the height. So here we have height y2, here we have height y1. So potential energy is mass, gravity times height. So we wrote two equations for work, W on the left side and the right side, force times distance, and also kinetic energy change plus potential energy. So these two sides are same, therefore we can write force times distance is equal to kinetic energy plus potential energy change. So when I write that, left side we have force times distance and for work, and the right side we have kinetic energy change plus potential energy change. So now I'm going to move number P2s, V2s, and Y2s. The 2 means the variables on the side 2, and 1 means variables on the side 1. So once I separate 1 and 2 variables, I end up with this equation. So this equation we call Bernoulli equation, which is good for steady flow. We'll talk about steady flow, non-viscous, incompressible fluid. It has a pressure, velocity, and height. Pressure, velocity, and height relationship between two sides of a fluid. So let's take this as example. This figure we saw in previous slide. So here there's no height change because it's the same height, but it has a two different diameters. So if there's a no height in this initial equation, y1 and y2 is same. So I can cancel these two terms. Then I end up with P1 plus half rho B1 square equals P2 plus half rho V2 square. So it's a pressure difference and also speed difference. So we know speed here is greater than speed on the large opening. So which means if the speed is greater, which means pressure is lower. So pressure in this side is lower than the pressure on the side with the larger cross section. Okay, so that's one point. And if you go to the second figure, the cross sectional area is same. So which means speeds are same. So V1 and V2 are same, but it has a height change, Y1 and Y2. So we can rewrite this equation, P1 plus rho G Y1 equals P2 plus rho G Y2. Okay, if the Y2 is greater, which is on this side, side 2, the pressure is lower again. So if the Y is high, pressure is low. So we can use this equation for different applications. That's the reason we want to uh, uh, talk more about this equation, because this equation has a lot of applications. And next few slides, I will show you a couple of different applications we see day-to-day life, and this uh, follows this Bernoulli equation. Okay, so in this example, when this truck is not moving, this tarp on top of the trailer is flat. So we know both sides of this tarp has air molecules like this. Okay? So inside the trailer and outside top of the tarp has air molecules. And when the truck is start moving, the air molecules on top has the higher speed compared to the air molecules the inside. Okay, so which we know that if you have higher speed, we have a low pressure. Low pressure. So if there's a pressure difference, low pressure, high pressure. So if there's a pressure difference, we know this tarp bulge outside. So that's why you see a bulging, because there's a pressure difference. So similar application. So this is a cross section of airplane wing, and when the airplane is moving, the air molecules here has higher velocity compared to bottom. So therefore, here we have a high pressure, because high speed, low speed, which means high pressure, and then here we have low pressure. So because of the low pressure, we have a force. We call it lift force. It helps to lift the airplane above the ground. Okay, here's another application, a curving ball. If the ball is travel through the atmosphere without any spin, both sides of the ball, top and bottom, has a same speed. Therefore, it's not curving. But if the ball is spinning, and here we have higher speed compared to the molecules here. So therefore, if there's a speed change, which means the pressure change. So lower pressure, high pressure, lower pressure. So therefore, you have a force, and therefore, when you shoot the ball, you will see a trajectory or curve.